So how many of you already plan to go to university? You want to raise your hand? Come on, don't be shy. This is the way of testing my voice this morning, get her going, okay? How many of you plan to go to UND out of those who plan to go to university? How many of you plan to major in physics? That's why you're here. It's my job is to convince you to come here and major in physics. Now you might ask, why the heck would I want to major in physics? Especially because my first choice is not to major in physics. Well, the reason why I want you to come and major in physics is because we need you. We need the next generation of researchers. We need the next generation of people with ideas of things that we've never thought about up to this point in time. We need fresh blood. Now, why do you need that in physics? Physics has been around arguably for hundreds and hundreds of years. And in particular, when we talk about astronomy and astrophysics, well, people have been looking at the sky ever since they had the brains to wonder about the universe around them. So why do we need you today in 2019? This is why. Hopefully all of you had breakfast, because now we're going to talk about dessert. In particular, the cosmic pie. Now this cosmic pie shows you a breakdown of what we know about the universe. The one thing that's interesting in all of this is the fact when you look around, when you leave this room today, when you wander around your life outside of school after everything is finished and the day is over, the things that you see around you represent 5% of what's out there. 5%. In fact, everything we've been studying for the last several thousands of years, it represents 5% of the known universe. 5%. Well, what's the other 95%? Well, we give fancy labels to it. One label is called dark matter. Dark matter represents about 27% of the universe. The majority is what we call dark energy. Now, when you see dark here, you say, they must be linked. Dark matter and dark energy somehow linked together. I know of the most famous equation in all of physics. Does everybody know what that is? Let's write it on the blackboard. You ready? Help me out. E. What do you think the rest of it is? Equals, what's the rest? MC squared. So energy and mass somehow are related. So dark matter and dark energy, they have to be related. Not necessarily. In fact, the prevailing wisdom is they have nothing to do with each other. Yet they represent, as you can tell from our pie, 95% of the known universe. So what this means is that for thousands of years, and if you want to get picky, ever since the time of Galileo, over 400 years ago, people have been studying 5% of the universe. That means anyone that you know of that's in chemistry, what they do is completely irrelevant. It only deals with 5% of the universe. Now, don't tell your chemistry friends that. And then they'll send me email and stuff, right? Okay, I don't want that. But when you think about it, most of the universe is yet to be explored. In fact, most of the universe is yet to be understood. That's why we need you. Now, where did all this stuff come from? If we don't understand what dark matter is, and we don't have a clue what dark energy is, how do we know it even exists? Well, actually, this story goes back nearly 100 years now. Way back in early 1930s. There was a very charismatic astronomer who was working at Caltech at the time, Fritz Zwicky. He was the type of guy that if you were walking down the hallway, even though you were a colleague, if you seen him coming towards you, you found some excuse to go somewhere else, like in the bathroom or some other office. You didn't want to cross paths. He was a mean guy, so they say. But Fritz Zwicky stumbled upon something extremely exciting. He discovered that there was a part of our universe that was completely invisible. You couldn't see it. You couldn't taste it. You couldn't touch it. But you knew it was there because it had gravity. Now, gravity comes in one flavor. Unlike ice cream, thankfully, it is always an attractive force. And so it is the gravitational influence of this unseen stuff that we figured that it even exists to begin with. And you might say, well, how does that work? The way you're thinking about it is this. Imagine you go to a movie theater. And it's one of those types where it's a live production. and people are up there dancing. Now, it just so happens that when you look up, there's a woman who's dressed completely in white and a guy who's dancing with her dressed completely in black. And behind them is the dark screen. And of course, the lighting of the theater is such that you can just see the people up on the stage dancing. Now, if they can do it right with the tricks of light and so on, you can actually see the woman holding on to the man, spiraling around in a circle, and she's leaning back. But you can't see the man. He's camouflaged, if you like, with the background. But you know intuitively, there's no way somebody can lean back like that without falling over. They're holding on to somebody, going around in a circle. In other words, you can detect the presence of something indirectly. In this case, in terms of dark matter, by noting its gravitational influence. In fact, Fred Zwicky noticed that the motion of galaxies, which are a collection of stars, gas, and dust, in this area that we call the Coma cluster, it's a cluster of galaxies, those galaxies were moving too fast. They were moving faster than the local speed limit. Now, the only way that galaxies can move faster than what they should is that either A, they are moving apart from each other, so if I come back, sometime in the future and look at this system of galaxies, it would be more diffuse, more spread apart. Or there's more matter there than what I can see. Now, how do you measure the motion of galaxies? The way to do it is something simple, something that we call the Doppler effect. In fact, any source of waves, if it's moving towards you, the wavelengths that you observed are actually shorter than if the source were stationary. If the source of waves is moving away from you, the wavelengths get stretched out. And you know how this works for sound. You hear it all the time. If you're standing on the side of the road trying to fix a tire in the middle of the night, and a car is coming, you're like, oh, thank God, because I don't have any way to take off the lug nuts or something, right? My wrench is at home. And you hear a car approaching. What's it sound like? And of course, if they're not friendly, they'll just pass right by. And what's that noise effect that you hear? That's a change in pitch due to the Doppler effect. As the sound of the car, as it's approaching, has a higher pitch, a shorter wavelength. And when it goes by, it's moving away, those wavelengths get stretched out. And you hear that as a lower pitch. And so that change in pitch is what gives you that characteristic, especially if you go to NASCAR, right? You'll hear that all the time when they pass you. It's the motion, the relative motion that we can measure by looking, in this case, at the light that these galaxies emit. When you look at the light coming from these galaxies, you find that it's either shifted shortward or longward, depending on the relative motion toward or away from you. And from this, we can then measure the motion of galaxies in galaxy clusters and tell, in this case, that there's way more mass there than what you can see. This matter, by the way, doesn't emit light. And you might say, well, you're not looking in the right spot. You're only looking in optical light. We know there's a lot more out there than that. There's radio and gamma rays and X-rays and microwaves and infrared and ultraviolet. But when you look there, you don't find anything. Dark matter doesn't reflect light. It doesn't emit light as far as we can tell. It's only known because of its gravitational influence in the environment around it. So it's a complete mystery. What is this stuff? What's it made out of it? Is it made up of butter? What is it, right? What is this stuff that's out there? Well, in the 1930s, when Fred Zwicky first proposed that there was this dark matter that didn't give off light, people laughed at him. Like I said, he was this unfriendly soul, and everybody would jump on him if he published something, and people said, you're a crazy guy. That's the reason why people don't want to be friends with you. Well, it turns out he was right, of course. But we had to wait a while. In fact, we had to wait until the 1970s and 80s before other scientists discovered dark matter as well. If you like, the rediscovery of dark matter. An important work was done by Vera Rubin. She passed away just a few years ago, and the big push prior to when she passed away was to try to get her awarded the Nobel Prize in Physics for her discovery, if you like, of profound evidence for the existence of dark matter. And what was this profound evidence? It's the fact that objects moving around the center of our galaxy, and it turns out in mostly all other galaxies in the universe, they don't obey the laws as we know them. And that laws is such that the orbits of stars, for example, going around the center of the Milky Way should have well-defined shapes. And they don't. For example, when you look at the outskirts of our galaxy, so on this figure here, we have how fast objects are moving like stars, are orbiting around the center of our Milky Way. On the x-axis here is distance from the center of the galaxy. When you're on the outskirts of the galaxy, so you're way off on the right of this plot, you find things are moving too fast. This is the orbit that stars would have. This is the orbit they should have. There is a large discrepancy. Now, what is that discrepancy? That's evidence for the fact that our galaxy is embedded within a large halo of dark matter. And it is the gravitational attraction or influence of that dark matter that causes the stars to have the orbits that we would not expect. So in order, if you like, to understand the motion of things in our galaxy, you have to add dark matter. It doesn't work without it. It's a necessity. Well, is there other observations or evidence for dark matter? Yes, there is. Here's another example. It turns out that looking at these galaxy clusters, which I mentioned before, that Fred Zwicky looked at, that when we developed X-ray telescopes, we discovered that these galaxy clusters shine at X-ray wavelengths. They give off X-rays. Now, where does those X-rays come from? They come from the fact that embedded within these galaxy clusters is hot gas. And what do I mean by hot gas? I mean gas that has a temperature of tens to hundreds of millions of degrees. Very, very hot. If you had a can of gas in front of you at that temperature, you don't want to look at it. Number one, it gives off X-rays, so stay away, right? It's dangerous. Now, in order to hold on to that hot gas, there has to be enough gravity. And so by examining, for example, how much of this hot gas we find in these galaxy clusters, like the image on the left here, that tells us then how much matter in total there must be in these galaxy clusters. We can see individual galaxies. We can estimate how much mass each of these galaxies have. But when we add it all together, it's not enough to hold on to that hot gas. There has to be more. And that more is the dark matter. With the addition of dark matter, there is enough matter to hold on to that hot gas. Is there other evidence? Yes, there's other evidence for dark matter. Here's one here. When you look at this image of the galaxy cluster that you see on the left, it's an image, by the way, taken with the Hubble Space Telescope. And if you look very carefully, one of the things that you'll notice are these streaks that you can see occasionally, these arc-like features. There's a beautiful one here, but there's several of them all around this galaxy cluster. And if you notice carefully, they are concentric. That is, they form an arc that goes around like part of a circle. And the center seems to be the center of the cluster, which is roughly here. So what are those things? What are those arc-like features? They're known as gravitational lenses. They are produced by matter. Matter, as Einstein tells us, warps space and time. And it's the warpage of space that causes background galaxies to be distorted. In fact, to be distorted in such a way that they give this appearance of these arcs. And by knowing the shape of the arcs, you can estimate how much matter you need to cause the curvature of space to give rise to those arcs. And it's a lot more than what you see if you count up the individual galaxies. More evidence for dark matter. Well, is dark matter just confined to galaxy clusters and individual galaxies? Well, no, we see dark matter everywhere. This is a study that was done looking over nearly 8 billion light years in distance. Now, what's a light year? It's the distance that light travels in 1 year. It's about 9 trillion kilometers or 6.5 trillion miles. And so we're looking over a large fraction of the universe when we're looking from the present day down here back to about 8 billion years in the past up here. And these clumps or shapes that you see here is a sort of a gross, if you like, mapping or survey of the amount of dark matter and where it is. It's everywhere. There is dark matter in this room, presumably. Is there more evidence for dark matter? Yes, there is. This is a map, if you like, or a survey of what the universe should look like if you put all the known laws of physics and you mix them up in a computer model and see the end result. It should match your universe, what you actually observe. If it doesn't, something's missing. If you don't add dark matter, it doesn't work. The model that we get from the computer doesn't match the observations. That was a real problem several decades ago until we realized, aha, we're missing something here. That's the dark matter. Let's put in the dark matter. Then you start matching what you see in terms of the observations, which is always a good thing, right? Nobody's going to care about your model if it doesn't match reality. That's the way science works. So the big question today, nearly 100 years after Zwicky made his first observation, is what the heck is this dark matter? You need something that has mass. Why? Because we know its presence due to its gravitational influence. There has to be gravity involved here. But it doesn't give off light, or at least it doesn't give it off to the point where we actually observe it. Maybe it's so faint and the objects are so far away on average that we just can't see it with our present technology. So there have been a number of suggestions. Maybe there's trillions and trillions of planets spread everywhere in the universe. And if you add up all that matter, then that would be the dark matter. If you use those type of arguments, you say, well, then what on average, where should be these planets today around us? And there should be a lot of them, even within our solar system, and yet we don't see them. There doesn't seem to be enough. And you can use that argument for anything. Maybe the dark matter is made up of hockey pucks. Now you might say, how can that be so? Well, it has matter, right? Each hockey puck has a certain weight associated with it, a certain amount of mass. Therefore, it attracts everything by gravity. But then you do the calculation, well, how many hockey pucks do you need to make up the dark matter? And it turns out you need so many that literally when the astronauts were on their way to the moon in the late 60s and early 70s, there should have been hockey pucks bouncing off the windows, right? That didn't happen. There's not enough of them out there. So you need something that's abundant enough that's going to make up the dark matter. And so you try all the normal things. Maybe black holes. It doesn't work. There's not enough of them. Maybe faint stars, intrinsically faint stars. Doesn't work. It's not enough of them. So today we boil down to a sort of small, if you like, list of candidates. We think the dark matter then is some type of subatomic particle. Now, the best candidate that we have, we give a name to it. We like to name things so we know what each other's talking about. We call them WIMPs. That stands for weakly interacting massive particles. Weakly interacting because as far as we can tell today, they only interact via gravity. That's it. So they got to have mass, but we don't know anything else about their properties. So it makes it very hard to detect them. So people use fancy particle detectors, things that are put underground to shield them from cosmic rays, from other particles that we know do exist, to try to find something that's extremely elusive. So far, no luck. The best sort of results that have come out to date is this experiment that uses xenon atoms. And it puts very tight constraints on what the dark matter particle is. But so far, no luck. Well, if you can't detect them, maybe we can make these things in the laboratory. We tried. Doesn't work. The latest experiment to try this is the Large Hadron Collider that you might have heard about in Europe. The end result of all of this is that today, in March 2019, if you were to ask me, what is the dark matter? I would say, I don't know. And we don't know. We're still looking. We need people to help in this search. Maybe we won't find the answer to this puzzle for another 20 years. That's your time. That's when you can evolve. That's when your ideas can make an impact. We need you. Is this it? No, this is not it. There are other mysteries in the universe that beg for an explanation. The other one is called dark energy. Our modern day understanding of the universe as a whole, cosmology, comes from Albert Einstein in his general theory of relativity. It's over 100 years old now. When Einstein first applied his ideas to the universe, what he discovered was that the universe should either be expanding or collapsing. And in those days, back in 1915 or so, astronomers told him the universe was static. It wasn't expanding, it wasn't collapsing. So Einstein said, you know, there's something wrong with my idea here. I don't understand this. So he introduced an extra term here, a mathematical symbol, that today represents dark energy. Now, Einstein quickly made a mistake and got rid of it because a few years later, it was discovered by Edwin Hubble that the universe is in a state of expansion. So Einstein said, I didn't need to add that extra term to my equation. I could have left it out. And in some sense, I could have predicted that the universe should be either expanding or collapsing. One of the best or greatest prediction of all humankind. Didn't do that. Didn't trust his equations enough. Einstein, not trusting his own work, unheard of. But it happens. We're humans. In fact, to understand the universe was to understand what type of geometry does the universe have. For many, many years, we figured it's either a flat universe, what we call an open universe, or a closed universe. Just think of geometry, the surface of a sphere, the surface of a saddle, the surface of a piece of paper, a flat plane. Which type of universe do we live in? It depends on how much matter and energy is in our universe. So let's add it all up. When you add it all up, what do we have? Well, we have ordinary matter, and we have the dark matter, of course. We can't forget about that. When you add it all up, we have a certain value, which represents this open type of universe, which means the universe essentially expands forever. And that expansion rate slows down with time. But it never comes to a standstill. It will always expand. It'll just get less and less and less as time goes forward. But in 1998, everything changed. And what happened in 1998 then, through the use of exploding stars, which you see in front of you here, we discovered that the universe expansion rate is not slowing down. No, it's not. It's actually speeding up. It's accelerating. It's as if there's some other force in nature that we didn't know exists prior to this time that we're pushing things away from each other, going against gravity, anti-gravity, if you like. That was a complete shock in some sense. In other sense, of course, once you know it's there, it's like, yeah, well, if you look at the data or observations that were taken 20 years ago, that would have made better sense if I would have thought about this dark energy. But of course, nobody put it together until 1998. And the people who were responsible for that won the Nobel Prize in Physics in 2011. Even though we don't know what the dark energy is, they still win the Nobel Prize because we know of its existence. We see its influence on things that we know about in the universe. So we're left with this fundamental question today: what is dark energy? What is this force? Where does it come from? There are various ideas people have. None of it, after over 20 years of theorists and publishing papers that literally stack from the floor up to the ceiling here, nobody has the right idea. Nobody's been able to solve this mystery of dark energy. If you can't solve it, you don't know what it is, what's the next best thing you can do? Study it to death. Look at it. Look at your universe. Figure out how much dark energy is there. Does it change with time? Was there more dark energy in the past and there'll be more in the future? How does it all work? Well, part of this is taking observations. And this is a project called the Dark Energy Survey that I've been part of for many years now to try to get a better handle or grip on the amount of dark energy in our universe. The recent results that have come out a few months ago tells us that this dark energy, this accelerated universe, is very similar to what Einstein proposed, even though he did it, if you like, from the wrong point of view. And the fact that he tried to tweak his equations to give rise to a universe that doesn't expand or collapse, which we know is not the universe we live in. But yet, Einstein's introduction of that fudge factor seems to actually describe our universe that we do live in. But what is the dark energy? I don't know. Nobody knows. We're in the same boat as we are with dark matter. So what do? We just study it to death. And so once you're done with one survey, you think of design a different experiment. Something that will give you an even better handle on the amount of dark energy. And we do that. This is the new one that's coming out in a few years called the Large Synodic Survey Telescope. It's to look at and measure the universe so we get a good handle on dark energy. And if that doesn't work, let's put a telescope in space that's dedicated to these observations so we get a good handle of what the dark energy is. And we're designing those telescopes now. But we need people to analyze the data. We need new ideas. If we're going to understand the universe, at least the majority, 95% of which we don't know today, we need you. We need you then to pick up the reins, to move things forward in the future. And if you want to do that, please come to UND. Please become a physics major if this interests you at all. We need fresh ideas. We are begging for new ideas to get us out of this, if you like, situation where 95% of the universe then is something that we can't explain. We have a lot of work to do. Physics is not a dead subject. It is one in which is very much is at the forefront of our thinking and thought processes today. Please enjoy yourself. If you have any questions at all, I'll be around today. If not, thank you very much for listening. Thanks. Any questions? If not, I guess there will be others in the back of the room who will lead you to your next destination.